Hey, this is Dr. B here, and let's take a look at some graphs. Graphs are a great way to show a lot of information in a very simple format. For chemists, and that's the angle we're going with here, spectra are graphs in just another form. So let's use this as a basis for understanding some spectroscopy by looking at a couple of graphs. I really like these two graphs, and I have to thank my fellow teacher Lou Monaco for bringing this to my attention. Take a look at these two graphs. I won't say much. Pause it if you will, and then tell me what you think these graphs are saying that you might find relevant. Okay, hope you paused. Here's what I find relevant about them. Number one, the population of planet Earth at first blush looks like it is just totally out of control. Look at how it just went up straight. You'll find graphs on the internet that don't even do this little curve at the top, which leads you to some sort of dire predictions. However, this one does show this little curve, and if you interpolate here, meaning go within those points, you'll see that perhaps things aren't as grim as you might imagine. It is starting to curve out. In fact, most experts, in fact, people like my friend Lou Monaco, who teaches AP Human Geography, are convinced that the population of planet Earth will level off in the next 100 or maybe 200 years at somewhere, well, it looks like under. Yeah, these don't really line up. Look at this, 10 billion here, 10 more than 10 billion there. Regardless, this graph indicates that it should level off at some point. Fine. And there's details within here that some populations are growing faster than others, or perhaps it's almost like they're slowing down at different rates. Okay, I find that interesting, and I think that's a good indication of how graphs can give you a lot of information. So, why are graphs awesome? They can quickly make sense of data. You do have to look for some inconsistencies here. It might be relevant. This graph to me is far less relevant than this one. They can reveal some trends, some very obvious trends. And trends mean two things. Mean that you can go within the data points, like within here, to interpolate, to try to show what it might be for data that where it wasn't even measured. It's likely to be here, even if you only have this point and that point. But even more interesting, at least to me, is that you can extrapolate. And look at this graph here. We're currently around here. And so it's extrapolating beyond that. These aren't real data points. These are just extrapolated data points. Will they hold true? Maybe, maybe not. If you follow the trend, yes, they will. And if you're going to write some useful graphs, here's some things to keep in mind. Place the thing that you choose to change on the horizontal part of your graph. I believe they call that the x-axis. Fine. I believe they call that the independent variable, a term that I really don't like at all. It's what you're choosing to vary. And when you do that, you can check out something else. That'll be the result, right? That'll be the population as a function of time. As time goes on, the population is increasing. We call that part the vertical axis, right? But if you want to be fancy, you can call it the y-axis. And if you want to be really fancy and confuse people, you can call that the dependent variable. Fine. You better choose your ranges carefully, because if you chose to block this off, just choose this range from the beginning of time till, here, you're going to get incomplete luck. I mean, this little curve here is really important to me, so choose your ranges carefully. And here's some very useful ranges where you're really seeing what's happening. And finally, you could consider error bars. You don't see them here, but boy, I love them when people throw them in, because a lot of time, especially in the scientific world, you get a lot of bounce. So you'll get a data point that bounces up, but you know that the data is so fuzzy because of the big error bars that it doesn't matter. So that's something to keep in mind. That's an introduction to graphs as it applies to science. Now let's continue to take a look at a few graphs and tell me what you think they mean to you. I think that the real point of a useful graph is to try to make a simple salient point, and each one of these do, including this set of two here. So have a look at them, and in your simplest words, you might have saw that, tell me what each graph is saying to you. In the first one, we have volume as a function of temperature. And we see that as the temperature goes up, the volume goes up. But if you are looking at this, the volume is going down for a gas. And it's going down, down, down. And at some point, it hits zero. Now, you can't have a negative volume. Similarly, perhaps you can't have a negative temperature. That might not make sense to you because this is a negative unit, but perhaps there is a temperature at which you cannot get colder. And that must be the temperature at which you have no more volume. So this is a wonderful example of how to extrapolate a straight line to come up with a minimum. Nothing can get colder than minus 273 degrees Celsius, end of story. And I can show you other graphs that show that this is regardless of the pressure as well. How do we do that? By extrapolation. Here's another graph. And if you look at these numbers, say 27, 27, 50, 50, 100, 100. So if we do grams divided by milliliters, we'd always get a value of 1. That must mean that the density, meaning grams divided by milliliters, of water is 1.0 grams per milliliter at room temperature, regardless of your volume, right? And that's a nice intensive property. It's a nice useful thing. And in fact, they tune these units so that that is true because the water is so common, it's nice to have a value of like 1.0. Last one shows a couple of curves for the same thing. We're measuring pressure as a function of volume. And as volume is increasing, the pressure is decreasing, but not down to zero. It might be, confusing to look at this at first because does it matter that it's a curve? What if it was a straight line? But now here's one that's really clean, right? Instead of doing volume, let's take the inverse of the volume, and you get a perfectly straight line. So that must mean that as the pressure is increasing, the inverse of the volume is increasing. Now that might sound weird, a little bit weird, but isn't that the same thing that is saying as pressure goes up, volume goes down proportionally? That's a nice thing. That's known as Boyle's law. As the pressure increasing, the volume decreases. How did we know that? By taking the slope of the inverse. Here we took the slope of just mass versus volume. Here we take the slope of mass versus 1 over volume. And nice things to know. We're going to apply this in this unit to understand some other types of graphs, and I thought I'd give you a little preview. Here's some graphs we'll be learning how to interpret. This one is known as the mass spectrum of a substance. Here's the infrared spectrum of the same substance, and here's the NMR spectrum of also the same substance. We'll be learning how to use these and interpret these graphs in order to identify unknown substances. This is an introduction to graphing.